Hello guys, today we're going to be working on lab 3. First, we are tasked with reviewing this circuit right here. In order to understand the circuit, we have 3 inputs, X1, X2, and S, and it is followed by 4 gates. We have a NOT gate, which is essentially an inverter gate, so if S is 1, when it goes through this gate, it will become 0, and vice versa. We then have the AND here, and an AND gate here. Um, X1, 1, and then if S is 0, it will become 1, and that is the only way this gate will work. Which is opposite here, so top gate only works when S is 0, and bottom gate only works when S is 1. Here we have a OR gate, so once both AND gates are done, they will feed off into the OR gate, and this will cause either if this top one is 1, or if this one is 1, it will give us a value of 1, and therefore F will be 1. Here we can see the truth table for this. We can have a few examples run through here, such as 0, 1, 0, 0. We would have this as 0, so this will automatically be no, or 0. 1, this will be 1, and since S is 0, so then this will both be 0, 0, which will be F is equal to 0 here. Or we can have something such as this, where it is 1, 0, 0, 1, where we have this is 1, this is 0, but since it goes to the inverter, it becomes 1, so 1, 1, which will, in the OR gate, automatically be F equals 1. Moving on to the Vivado, we're able to see here, I added this so we can compare directly. We have the mystery design source. We have X1, X2, and S as inputs, and we have F as the outputs. Here we have all 4 gates corresponding, so not with the S, and which will give us A1, and this will be given by X1 and not S, and then which is the top gate, and the bottom gate is A2, which is given by the answer for X2 and S. And the end, we have the OR gate, which is the value of F given by A1 and A2, which is both AND gates right here. Moving on, we have the simulation sources, which we will move on to here. Same thing, our inputs and our outputs. And we have everything set up here, so we are able to have the simulation. So every single value in the truth table will be given on here. So from here, we move on to run simulation and zoom out. This is already zoomed out, but we would zoom out to 10 nanoseconds, which that is what we had established right here. So we move on and we compare it directly to the truth table. So we are actually able to tell if the Verilog implementation is done accurately for the circuit by comparing the values directly given by the wavelength here and the truth table. So here we have zeros all across the board, zeros all across the board. We have 0, 0, 1, 0, 0, 0, 1, 0, 0, 1, 0, 0, 0, 1, 0, 0, 0, 1, 1, 1, 0, 1, 1, 1. We have 1, 0, 0, 1, 1, 0, 0, 1, 1, 0, 1, 0, 1, 0, 1, 0, 1, 1, 0, 1, 1, 1, 0, 1, and the final is all ones, and we have all ones. So after comparing the wavelength and the truth table, we are able to see that both the, or just the the Verilog implementation is correct. From here, we are also able to look at the schematic and the RTL analysis, and we're actually able to compare this with the original schematic given to us. Here, we're able to compare this schematic with this one. We have the three inputs and the output. We have gate 1, gate 2, or gate and gate 1 and gate 2, which would be AND gate 1 and gate 2, and the OR gate here. We do not see the same inverter or NOT gate, but we are able to see the little circle right here, which we know represents the NOT of the S going into this AND. Moving on to the second task, we are given these three equations describing a circuit, and we have A, B, C, and D as our inputs. We have out 2 and out 3 as an output, but then we also have them as an input as they create um, out 1. Here we have the truth table created for every single value. We're able to decipher what it is by the power of 2, or the power of however many values there are. So it's 2 by, and then since there's 4, it's 2 to the 4th power. So it would give us 16 different values on here. A quick rundown of how these equations work. So for out 2, it's AC plus BD. For the first part, it it either has to be either both of these are 1, both A and C are 1, or both B and D are 1 in order for us to receive full 1. So if this is 1 and this is 0, this would both be 1. If it's 1 and 1, it's 1. And if it's 0, 1, it's also 1. For out 3, we have A plus not C. So, and then we have here, we have not B plus D. For equation 3, at least one of them on each side of the parentheses has to be 1 since they are multiplied. So if one of them is 0, so if the total of this is 0, if they're both 0, and if they're both 0 here, the whole equation, it would be yielding a 0. Otherwise, we would receive a 1 for here. And for out 1, it's just the addition of both out 2 and out 3 up here. So we would be getting, if this is 1, this is 0, it's still 1. This is 0, this is 1, it's still 1. And if both of these are 0, it's the only way out 1 is 0. An example of this, looking at the truth table, would be for all of these to be 0. So this line right here would have all inputs as 0. So for out 2, we'd have 0, 0 plus 0, 0, which would equal to 0. So out 2 would be 0. Out 2 is 0. Here we have 0 plus not C, which is 0, and would become 1. So this is 1. B, which is all, or yeah, B, which is not, which is 0, would become not B, which is 1 and 0. So we have 1 and 1. So out 3 is 1. And since we have 1 plus 0, we have 1. Another example of this would be 0, 1, 0, 1, which yields all three to be 1. So we have 0, 1, 0, 1. So out 2 would be 1 right here. And then we have 0, 1, 0, 1, which would also give us 1, out 3, 1, and then 1 plus 1 is still 1. So we get out as 1. Moving on to the Verilog design, we're able to see the module as replicator as stated on the lab. And we're able to break these equations down into here. We have the 4 inputs and the 3 outputs we had stated before. So the first block here is the out2 equation, which AC is considered, the multiplication is considered an AND gate. So we have T1, which is both of these, and T2, another AND gate here, and the plus sign would be the OR. So out2, which would be our output value, and then it would be T1 or T2, which is the ones we found here. For the second equation, we have this block right here, and we have not C, the value is for not C is Cn, and not B, Bn, and we have C and B, which would be the ones stated here and here. And then once that is done, we will feed it into the overall each parentheses, which, as we have stated in out2, is an OR when there is an addition. So we have T3 is equal to A and not C, and T4 is equal to not B and D. From there, it is multiplied for out3. So we had stated that in the top one, A and C, it is an AND gate. So we have the value for out3, and that is computed using the values for the last 2 OR gates right here. Now, since this is an addition, for out1, we had set out1 to be the addition or the OR for out2 and out3. Moving on to the simulation source, we have once again set up every single value that we have gotten in the truth table on here with a difference of 10 nanoseconds in order to be able to see the different values within the wavelength. So once we run the simulation and we know it is done correctly, we will see all the values populated like we have before in the exact same order, and we can go one by one checking every single value. I will do random ones just to check for accuracy. We have 0, 0, 0, 0, 1, 0, 1 go into the truth table, all zeros, 1, 0, 1. And then we can move on to, say here, we have 0, 0, 1, 1, all zeros. We have 0, 0, 1, 1, all zeros. Move to a random one here, 0, 1, 1, 0, all zeros. 0, 1, 1, 0, also all zeros. And the one right after, we have 0, 3 ones, and we have 1, 1, 0. Here we have 0, 3 ones, same thing, 1, 1, 0. And then we can move on to the one where A is 1 on this side. And also check here. We have 1, 0, 0, 1. We have 1, 1, 0, 0, 1, and it's 101, 101, 1, 1, 0, 1. We have 1, 1, 0, 1, all 3 ones, all 3 ones. And we can confirm that for every single value within the wavelength. Here, once again, we are able to tell that the implementation for this was for the replicator was done properly, since everything in the wavelength corresponds directly with what corresponds on the truth table. So seeing a direct comparison between this and this, and them both being exactly alike, knows that we have implemented this correctly. Another thing is we can run the RTL analysis to give us this circuit right here. Here we can see the equations getting settled out in an actual circuit. We have both AND equations and the OR, which would be AC AND, BD AND, and then the resulting value of this in an OR in the plus value. Down here we have the OR, and we do have the NOT gates included in there. And then those would get fed onto the AND, which is the multiplying here. And they would each feed out to out 3 or out 2. And then we would also have them feed off into this OR gate, which would be the resulting out 1 value. And that's how we're also able to compare that this was done correctly, seeing this and seeing the circuit directly represent the equations.